All right, let's just dive right in. Welcome to this explainer, where we're going to decode the invisible forces that literally hold our entire universe together. We're talking about how atoms interact, bond, and basically build a whole shebang around us.
Now, to really wrap our heads around how atoms actually work, I want you to picture a classic classroom scenario. Have you ever shown up to a class or maybe a meeting and realized you completely forgot a pen? You desperately need one, right? Now imagine the person sitting right next to you happens to have an extra one. So, what happens next?
Well, naturally, you negotiate. Maybe your classmate just gives you their extra pen outright, or maybe you kind of sit close and share a pen back and forth so you can both get your work done. Either way, through exchanging or sharing, both of your needs are met. You're both satisfied. Well, believe it or not, atoms do the exact same thing. They're just trying to find their most thermodynamically stable state, which, in chemistry, we just call stability.
So, let's start with Section 1, the quest for stability. Notice the magic number here, 8. You see, in the atomic world, stability has a very specific definition. Most atoms are on this relentless quest to get exactly 8 electrons in their outer, or valence, shell. It's known as the octet rule. Once they hit that lucky number 8, they achieve perfect, happy stability. And they will absolutely negotiate with any other atoms they can find just to get there.
Moving on to Section 2, ionic, give and take.
So, ionic bonds generally happen between metals and nonmetals. And honestly, the absolute easiest way to remember how this works is just the phrase, I give. Think back to our classroom analogy for a second. This is the scenario where your classmate simply gives you their extra pen so you both have exactly what you need. One atom just transfers an electron completely over to another.
Let's look at how this actually builds using sodium and chlorine as our examples. Okay, step 1 is looking at the electronic configuration. Sodium has 11 electrons, which means it has one lonely extra electron hanging out in its valence shell. Chlorine, on the other hand, has 17 electrons, meaning it has 7 in its valence shell. It is desperately seeking just one more to reach that magic number 8. So we get to step 2, electron transfer. That electron literally moves completely from the giver, sodium, to the taker, chlorine, which naturally leads us to step 3, ion formation.
And this resulting ion formation creates a massive electrostatic attraction. Think about it. Because sodium lost a negatively charged electron, it becomes a positive ion. Because chlorine gained one, it becomes a negative ion. And as we all know, opposite charges attract. This intense attraction between the positive and negative ions creates an incredibly strong ionic bond. Actually, this exact process is what forms sodium chloride, which you probably know better as common table salt. And because this bond is just so strong, it results in compounds with super high melting and boiling points.
All right, Section 3, covalent, sharing is caring.
Notice the stark contrast in the approach here. While the ionic bond says, hey, take my electron, the covalent bond says, let's share. Covalent bonds happen between two nonmetals. So going back to our pen analogy, this is when both of you need a pen, but neither of you has an extra one to give away. You literally cannot afford to lose the pen you currently have. So you have to work together.
The memory trick here is simple. We share. By sharing electrons, both atoms can actually count those shared electrons toward their own valence shell. So through sharing, all the atoms involved become completely stable at the exact same time, without anyone having to permanently lose a piece of themselves. It's a total win-win.
Take a look at this structural formula for water, H2O. Oxygen has 6 electrons in its valence shell, right? So it needs 2 more. Hydrogen has only 1 electron, and it wants 1 more to be full. So what happens? The single oxygen atom shares electrons with 2 different hydrogen atoms. Those lines you see right between the H and the O, they represent that shared pair of electrons. That's your covalent bond. Now everyone is full, happy, and stable.
But what's really amazing is that atoms don't just stop at sharing one pair of electrons. Notice how hydrogen stops at sharing one pair, making a single covalent bond. But oxygen gas, O2, actually shares 2 pairs, creating a double covalent bond. And nitrogen gas, N2, it shares 3 pairs of electrons. That triple covalent bond is literally one of the strongest bonds found in nature. Now, as a general rule, covalent bonds typically result in compounds with lower melting points that generally don't conduct electricity.
Which brings us to Section 4, metallic, the free-for-all.
So metallic bonds happen exclusively between metal atoms. Imagine our classroom again, but this time, instead of trading or sharing pens directly with the person right next to you, every single student just throws their pens into the middle of the room for absolutely anyone to use.
In a metallic bond, metal atoms release their outer electrons, creating this massive sea of freely moving electrons that kind of just wash over all the positive metal ions, holding the whole structure together. And the absolutely crucial point here is that this exact atomic structure explains the real-world properties of metals. Because you have this massive pool of free-floating electrons that can just zip around easily, metals are incredibly good conductors of both heat and electricity. It's also exactly why metals are malleable, meaning they can be hammered out into sheets, and ductile, meaning they can be stretched out into thin wires.
And finally, Section 5, bonds in the real world.
Here is a nice, clear, visual summary of the 3 bonds we've covered. Honestly, I'd highly recommend pausing right here just to lock in your understanding. So you've got ionic bonds, formed by electron transfer between a metal and nonmetal, which conduct electricity when dissolved. Then you have covalent bonds, formed by electron sharing between nonmetals, which usually don't conduct. And lastly, you have metallic bonds, formed by that sea of free electrons strictly between metals, making them fantastic conductors.
If we actually map these bond types directly to items you interact with every single day, it really anchors the science right into reality. Like the table salt you put on your food, that's an ionic bond at work. The water you drink, covalent bonding. The copper wire inside your phone charger, yep, that's the metallic bond sea of electrons doing its thing. And the carbon dioxide you breathe out, that's just another covalent bond.
Now, whether you're brushing up for an exam or you just want a really reliable mental shortcut, here is the golden rule for quick identification. If you see a metal paired with a nonmetal, like sodium and chlorine, boom, it's an ionic bond. If you see a nonmetal paired with another nonmetal, like carbon and oxygen, it's a covalent bond. It really is that simple.
To wrap up this explainer, I want to leave you with this question to chew on. What would our universe actually look like if atoms never found a way to share or trade? I mean, without the simple act of one atom giving a literal piece of itself to another, or 2 atoms just agreeing to share what they have, there'd be no water, no salt, no air, no you, and no me. Literally everything we touch, breathe, and see is just the result of tiny microscopic objects endlessly striving for perfect balance. So maybe keep that in mind the next time someone asks to borrow your pen. Thanks for hanging out with me on this explainer. I'll catch you next time.